today is basically, well, why this all matters. Now, yesterday we talked about entropy and how the system's entropy is going to either stay constant or increase. All right, this is kind of a way that tells you basically the direction of energy flow. All right, like I used the example yesterday. If you were holding a hot cup of coffee, your hands are not going to get colder as the cup gets hotter. That's not the natural flow of things. Due to the entropy of the system, that is going to tell you the direction of energy flow. Now, what this becomes very important in is engines and efficiency. Right. Now, with that, a couple of different things here. Efficiency of an energy, or efficiency of any engine. When we did this last year, we did it as a lowercase e. Now it is the symbol epsilon, which kind of looks like a backwards facing 3, equals basically the work that you get out, absolute value of it, divided by the energy that gets put in, which is normally going to be done in terms of the high end of the heat. Okay? Now, what that means, what you get out, what you put in. So, when we talked about simple machines last year, and it was work output divided by work input, yeah, same exact thing. This number is always going to be smaller than this number, meaning that efficiency will always be less than 1 or 100%. There's no such thing as a 100% efficient engine. I used the general term that it can't happen due to friction last year. This year, this is the exact proof for it. Okay? Now, different cycles of engines are going to have different values. But there are two different things that we're going to look at today. There are engines where basically you put in heat, get out work, okay, or there are heat pumps. In which you put in work to move heat. Okay? Now, those are the two basic things that we're going to be working with here. Okay? Now, in all cases, you're going to have a couple of different things here. Normally, this is depicted as some type of hot reservoir. All right? Some type of cold reservoir. Now let's make this as an engine here. What's going to happen here is there's going to be temperature coming from the hot reservoir, in the form of Q, or heat, which goes into the engine. Some of that heat is going to be transferred into useful work. Now, all of it can't be used, so that means some of that heat is going to go into your cold reservoir. Now, basically, look at what's going on here. No matter what happens, there's going to be some heat lost in the system. Okay? You're not going to be able to get out everything that you put in. Because of that, this is going to come down to your cold reservoir. Now, as a consequence of this, your cold reservoir, as you add more heat to it, is going to get hotter. As this happens, when you get a smaller difference between your hot and your cold reservoir, you're going to get a less efficient engine. That's why cooling is so unbelievably important. When you look at things like a car, you need to have a radiator in order to have the heat moved around properly. So with that in mind, it is an absolute requirement. Now, the other alternative or the other possibility would be refrigeration. Now, this is kind of interesting how this goes. But still, same basic parts. You're going to have a hot reservoir. You're going to have a cold reservoir. Oh, wow, that was horrible. And that wasn't much better. But you've got a cold reservoir right here. Now, the thing that you're trying to do is get this to be as cold as possible. You want this to be very low. So what we need to do is we need to force the opposite of what would naturally happen. So anytime you're talking about refrigeration or air conditioning, anything like that, you're always trying to, rather than cool down what's inside, you're trying to pull the heat out of the inside. So that heat travels out from the cold reservoir due to work that is put into the system. And with this work and this here, you are going to get heat sent to the hot reservoir. Now, if any of you guys have ever reached behind a refrigerator, dropped something back there, anything like that, you will notice that the back of the refrigerator or under the refrigerator is insanely warm. Okay, that's why cockroaches tend to like to live down there, because it's a very, very good heat source. What happens is the cold reservoir inside of the refrigerator sends its heat out with help of the work from the outside. You obviously need to plug in a refrigerator to make it work. The electric power will cause freon or some type of gas to flow, which will allow the heat to transfer easily. And then it takes the heat from inside of the refrigerator and pumps it out. Same exact thing will happen with an air conditioner. If you put your hand over the air conditioner outlet, the stuff that goes outside of your house, it is very, very hot. Okay? That is because work has been done to pull the heat out of the air inside of the house. Okay? Now, this one was just short and sweet. All I want you guys to do right now is read pages 543 to 550 and that'll be it for today. I didn't give you a practice math problem to work on. I kind of got here a little bit later than I thought I would, so I wasn't able to get a full lesson in today. We will pick back up with the math of this tomorrow. All right? Just get through that reading, and tomorrow's going to start the math. Enjoy.